Good morning. So today we shall study the concept of voltage and current divider circuits. Depending on how we arrange the different components in the given circuit, we call the circuit as either the series circuit or a parallel circuit. If the different components in the given circuit are connected end to end, and across this combination, if we apply a source of EMF, such a circuit is called as a series circuit. And if the different components are connected such that one terminal of each component is connected together and the other ends are connected together, and across this combination, if we apply a source of EMF, such a circuit is said to be a parallel circuit. So when we connect the different resistors, for example, in series, and a source of EMF is applied across it, then whatever the voltage is applied across this combination is distributed over all the resistors connected in series. Depending on the potential drop across each resistor is found to depend on what is the value of that resistor. So such combination of the resistors is called the series combination, and in such series combination, since the voltages are distributed amongst the different resistors connected in the series circuit, is called as voltage divider circuit. However, if we connect number of resistors in parallel, and across this parallel combination, if a certain voltage source is connected, then that voltage source or source of EMF supplies certain current to the circuit, and depending on what are the values of the different resistors connected in the given circuit, that total current drawn from the source is found to be distributed in the different branches or through the different resistors. If the value of a particular resistor is large, a small current flows through it, and if the value of the given resistors is small, then a large current flows through it. So according to or as per the value of the resistor, the currents are distributed over the different branches in that parallel circuit, and hence such a circuit is called as current divider circuit. So let us discuss these circuits one by one. So let us first discuss the series circuit. Or it is also called as voltage divider circuit. Voltage divider circuit. Suppose we have a source of EMF, and across this source of EMF, say the three resistors are connected in series, that is end to end. Suppose this is the resistors R1, this is R2, and this is R3, and a voltage of say 12 volt is applied here. V is 12 volt. The value of the first resistance R1 is 1 kilo ohm, that of second is 2 kilo ohm, and the value of the third resistor is say equal to 3 kilo ohm. So when we connect these three resistors R1, R2 and R3 end to end, such that across this series combination we have applied a source of EMF. This is how we can represent the series circuit. Popular way of representing such a series circuit is again like this. So this is the positive terminal of the source of EMF and the three resistors R1, R2 and R3 connected like this. So this is R1, this is R2, this is R3. And only a positive terminal of the source is represented here and the ground. So this series combination of the three resistors is connected between the positive terminal of the source and the ground, so that whatever the current is sent by this source of EMF, same current is found to flow through all the three resistors. So the most important point to remember here is that if the given resistors are connected in series, then it is observed that the currents flowing through all the three resistors remains same. So this is the most important point that we must remember here. But depending on what are the values of the three resistors, the potential drop developed across each resistor is found to be different, such that if we calculate the potential drops across all the three resistors connected in the circuit here, and if we take the sum of the potential drops across these three resistors, it must be equal to the value of the applied EMF. So that is most important point that you must remember here. So in order to find out the potential drops developed across these three resistors, first we must know what is the current flowing through each resistor. In order to calculate the current I drawn from the source, what we should know is that we must know what is the total resistance of the circuit. Here, since all the three resistors are connected in series, the total resistance R of the circuit is found to be equal to the sum of the three resistors connected in circuit. So this is nothing but equal to the value of R1 is 1 kilo ohm, that of second R2 is 2 kilo ohm, and that of the third is 3 kilo ohm. So that the total resistance of the circuit is equal to 6 kilo ohm. So the applied voltage here is 12 volt and the total resistance of the circuit since is 6 kilo ohm. So the total current I drawn from the source is nothing but equal to V upon R. So this is equal to 12 volt divided by the total resistance is 6 into 10 raised to 3 ohm. So this is equal to 2 into 10 raised to minus 3 ampere, or this is equal to 2 milliampere. So the current drawn from the source is found to be equal to 2 milliampere. And when the current drawn from the source, since the same current flow through all these three resistors, we can find out the potential drops across these three resistors. These potential drops also can be obtained by using the potential divider formula. These potential drops, since are found to depend on the value of the resistors, and if the value of the resistance is small, a small potential drop will be developed across it, and if the value of the resistance is large, then a greater potential drop will be developed across it. So we can use the proportionate formula for the potentials across these three resistors, and either we can calculate the potential drops by using the simple Ohm's law. We have calculated the current flowing through each resistor is same, and we know the values of these resistors, so we can calculate the potential drops across these three resistors by using a simple Ohm's law. or else we can as well find out the potential drops across these three resistors by using the proportionate voltage division formula. According to the voltage divider formula, proportionate voltage divider formula, if we consider V1 is the potential drop across the first resistance R1 here, the value of the potential drop across R1 is given by R1 upon R, where R1 is the relative first resistor and R is the total resistance of the circuit. R is the total resistance of the circuit. Multiplied by the potential drop applied across this series combination. So this is nothing but V upon R, and this V upon R is nothing but by the current drawn from the source, that is nothing but the current going through the resistance R. So it is one and the same thing. Either you can calculate V1 by taking the product of I into R1, or you can calculate by using this proportionate voltage formula. It is one and the same thing. So this is equal to R1 is 1 kilo ohm divided by the total resistance of the circuit is 6 kilo ohm multiplied by the applied voltage is 12 volt. So this is 12 by 6, so it is equal to 2 volt. So the potential of V1 across R1 is equal to 2 volt. Similarly, we can find out the potential drop across the second resistance R2 in the combination, and V2 is equal to again R2 upon R multiplied by V, the applied voltage. R2 is 2 kilo ohm, so this is equal to 2 upon 6 multiplied by 12 volt. So this is equal to 4. This is equal to 4. And the potential drop across R3, say is equal to V3, will be equal to R3 upon R multiplied by V. So this is equal to R3 is 3 kilo ohm divided by 6 into 12. So this is equal to 6. So the potential drop across R1 is 2 volt, potential drop across R2 is 4 volt, and that across R3 is 6 volt. Therefore, if we take the sum of V1, V2 and V3, this is nothing but equal to 2 plus 4 plus 6. So this is 12 volt, which is nothing but equal to the applied voltage. This is the applied voltage. So what we observe here is that in case of the series circuit, whatever the voltage is applied with the help of the source of EMF, that voltage gets distributed over all the resistors connected in series combination. So this is called as voltage divider. This is called voltage divider circuit. So the applied voltage gets divided over all the resistors connected in the series combination, and the value of the voltage drop produced across a particular resistor is found to depend on the value of the resistor in the circuit, or in the value of that resistor. So let us see how to this voltage divider series voltage circuit also can be used to obtain the series voltage dividers. So for that purpose, let us consider we have another arrangement. Suppose we have the two resistors connected in series. So this is the first resistor and the second resistance, and the source of EMF is applied across this series combination. So with the help of this single source, say the value of this single here is say 10 volt, and we can obtain the multiple voltages with the help of this single source of meter. See, this is the first resistance R1 and the second resistance R2. The value of the first resistance R1 is say 15 ohm, and that of the second resistor is 5 ohm. So this is the point A, this is the point B, and this is the point C. Now, since the point C is directly connected to the negative terminal of the source and the point A is connected to the positive terminal of the source, so what we can say here is that the point A is at a potential of plus 10 volt with respect to the point C. With respect to the point C, the point A is at a potential of plus 10 volts. What will be potential at point B? To find out the potential at the point B, we should first calculate what is the potential drop across the resistance R1. To find out the potential drop across R1, we must know the current flowing through this resistance R1. And to find out the current flowing through this resistance R1, we should know the total resistance of this series circuit. So, the total resistance R of the series circuit is nothing but equal to the sum of the two resistors R1 and R2 connected in the combination. R1 is 15 ohm and R2 is 5 ohm, so that the total resistance of the circuit works out to be equal to 20 ohm. So, knowing the total resistance of the circuit, now we can use the potential divider formula to find out the potential drop across R1 and potential drop across R2. Let V1 is the potential drop across R1. V across R1 is equal to V1, and this will be given by R1 upon R into V. So R1 is 15 ohm divided by the total resistance of the circuit is 20 ohm multiplied by the applied voltage is 10 ohm. So this works out to be equal to 7.5. The potential drop across the resistance R1 works out to be equal to 7.5. Whereas the potential drop across R2 is equal to R2 upon R2. So this is equal to R2 is 5 ohm divided by R is 20 ohm multiplied by the other voltage is 10 volt. So this is equal to 2.1. So we have obtained the potential drops across R1 and R2. So here what we can say is that the potential at the point B with respect to point C is 2.5 volt. Whereas, so for that purpose here the point C is considered to be at 0 volt. So with respect to the point C, the point B is at a potential of 2.5 plus 2.5, and the point A is at a potential of 10 with respect to the point C. So from a single source, now we can have the three different potentials for us which we can use across a given load resistance. So what are these three voltages available to us? The three voltages available to us are that the potential drop across the points A and C is 10 volt. So this is the, if we use the connection, if we connect the load resistance across the points A and C, then a voltage of 10 volts is available to us. If we connect a load resistance across the point B and C, we have a potential of 2.5 volt available across the load. And if we connect load across the points A and B, then a potential of 7.5 volt is available. So, from a single source of EMF, we have the three different voltages available for our choice to be applied across a load resistance. So, this kind of arrangement of the circuit is called as the series voltage divider. This is called as a series voltage divider. Now, if a certain open appears in the series circuit, what will happen? Let us see. If open appears in the given circuit, the open appears in the series circuit, what will happen? Suppose we have this source of EMF and the two resistors are connected in series across this source. So this is R1 and this is R2. And we have a source of EMF 10. Now, if open appears in this circuit, series circuit, what will happen? If the open appears in this branch between R1 and R, this is source of 10. This is the open between R1 and R2. So, if this circuit is broken, it means that if we measure the resistance between these two open terminals, this resistance is going to be infinite. This resistance across these open terminals is going to be infinite. So, if the resistance between these open terminals is infinite, will there be current flowing through the circuit? There will be no current. If there is no current flowing through this circuit, no potential drop will be developed across R1. Similarly, no potential drop will be developed across R2, such that whatever the voltage is applied here with the help of this source, all that voltage will appear across the open terminals. All that voltage will appear across the open terminals. So the potential drop here will be 10. So, no potential drops will be developed across the resistors R1 and R2 if the open appears in this circuit, and whatever the voltage is applied with the help of this source of EMF, all that voltage will appear across these open terminals, because there is no current flowing through the resistors R1 and R2. So that is what will happen if the open appears in the given circuit. Then let us see the concept of short in series circuit. If a certain resistance is short circuit, what will happen? Short in series circuit. Say we have a source of EMF and the two resistors R1 and R2 are connected in series. So this is resistance R1 and this is resistance R2. So this resistance is 2 ohm and this resistance R2 is 3 ohm. And if so this is the point A, the point B, short is put across the resistance R2, what will happen? So this is R1, this is R2, and a short is put between the points B and C, that is across the resistance R. This is again say 10. This is again 10. So if a short is put across the points B and C, that is the resistance R2 is short circuited. Directly we connect a copper wire between the points B and C, so that the effect of R2 is nullified. So if the effect of R2 is nullified, what will happen to the circuit? So if such a short is appearing in the given series circuit, the power drawn from the source increases tremendously, so that large current flow through the circuit, and due to the excessive current flowing through the circuit, the different components in the given circuit gets heated up, and if this current is very large, then on certain occasions it may so happen that some of the components may get burned off. Certain components may get burned off. So a care must be taken that such short is not made across the certain component in the series. That we can verify by calculating the powers in the circuit in the two different situations, before we put the short and after we put the short. Say P1 is the power in the circuit before we put the short across the resistance R. So this is the figure A and this is the figure B. So in figure A, the total resistance of the circuit is R1 plus R2, that is equal to 2 plus 3 equal to 5 ohm. And if a voltage source of 10 volt is applied across this series combination, then the current I flowing through the circuit will be equal to say this is I1, this is I1. Okay. So I1 is equal to 10 volt divided by 40. So this is 2 ampere. So the power P1 in the given circuit, when both the resistors R1 and R2 appearing in the circuit, will be equal to I1 square into R. So I1 square is 2 square multiplied by R. The total resistance of the circuit is 5. So this is 30 ampere. So in the given circuit, the power drawn from the source is equal to 20 ampere. However, in figure B, if we put the short between the terminals B and C, so that resistance R2 gets short circuited, then what will be the current I2 drawn from the source? The resistance R, the total resistance of the circuit is equal to R1 and is equal to 2 ohm only. So that the current I2 drawn from the source works out to be equal to 10 volt divided by 2 ohm. So it is equal to 5 amperes. So that the power P2 drawn from the source will be equal to I2 square into R. So this is equal to I2 square into R. So I2 is 5 ampere. So it's square multiplied by R, that is R1. R is 2 ohm. So this is equal to T. So the power in the circuit increases from 20 watt to 50 watt. So the power increases by about 2.5 times. The power run on the source or the power in the circuit increases 2.5 times. So the different components gets heated up due to this excessive power, and because of this there is a chance that some of the components in the circuit may get burned. So care must be taken, and to prevent such burning up of the components, we must use an electric fuse in the circuit, so that when such excessive current flow through the circuit, the fuse gets fused and the components and as well as the source of EMF also are protected from getting permanently damaged. So that is about this series circuit or the voltage divider circuits. Next we shall see the parallel circuit or the current divider circuits. Or current divider. If the different resistors are connected in a parallel, like this, one end of each resistor is connected together and the other ends are connected together, and across this series combination, if a certain source of EMF is applied, then let I is the total current drawn from the source. This is the resistance R1, this is the resistance R2. When this total current I appears at this point A or at the junction E, what will happen? That current will get distributed over the two branches. Let the part I1 flow through R1 and the part I2 flow through the resistance R2. So depending on what are the values of R1 and R2, this distribution of current will depend. If the value of resistance R1 is greater, then a small current will flow through R1, and if the value of resistance R2 is greater, then a small current will flow through R2 and greater current will flow through R1. So depending on what are the values of these resistors R1 and R2, the current distribution through these two resistors is going to be different. So let us consider the values of R1 and R2. For the sake of understanding, let the value of R1 is 2 kilo ohm and that of R2 is 4 kilo ohm. And a current of 9 milliampere is drawn from the source. A current of 9 milliampere is drawn from the source. Now, when these resistors R1 and R2 are connected in a parallel, then the most important point to be remembered in the parallel circuit is that the potential drop across each resistor in the parallel combination is found to remain same. The potential drop across each resistors connected in the parallel combination is found to remain same, whereas the currents flowing through the different resistors are found to be different. In case of series circuit, we have seen that the currents flowing through all the resistors remain same, whereas the potential drops across the resistors in series are different. Whereas in case of the parallel circuit, the potential drop across the two ends of this parallel combination is same, remains same as well as the applied voltage. Whereas depending on the value of the resistance, the currents through each resistors are going to be different. And for this reason, such a circuit is called as current divider circuit. Such a circuit is called as current divider circuit. So let us find out the values of the currents flowing through the different resistors connected in a parallel. Here, one point we must remember is that if we calculate the sum of the currents flowing through the different resistors connected in parallel, this sum of the currents must be equal to the total current I drawn from the source. That we can verify. So, these currents can be obtained by using the current divider formula. These currents can be obtained by using the inverse divider formula. In case of a series circuit, the potentials were going to be proportional to the value of the resistor. In case of the parallel circuit, the currents are going to be inversely proportional to the value of the resistor in a particular branch of that network. So, this current, inverse current formula is given by the current flowing through the resistance R2 is going to depend on the value of R1. So, I1 is equal to R2 upon R1 plus R2 into the total current I drawn from the source. The current to the first resistor R1 is equal to R2 upon R1 plus R2 into the total current I drawn from the source. So, and current I2 flowing through the resistance R2 is given by R1 upon R1 plus R2 into the total current I drawn from the source. So, that is the inverse formula for the calculation of the currents through the different resistors connected in parallel. So, these formulas for the voltage divider formula and the current divider formula are of great importance. These formulas we are going to make use while studying the three most important theorems in this chapter, that is the Thevenin theorem, Norton theorem and the superposition theorem. So, this concept of voltage divider circuits and current divider circuits is of great importance for studying these theorems. So, try to understand. So, here we can find out the values of I1 and I2 using the values of R1, R2 and the potential I drawn from the source. We can calculate I1 to be equal to R2. R2 is 4 kilo ohm divided by R1 plus R2 is 6 kilo ohm multiplied by I, the total current drawn from the source is 9 milliampere. So, this is 36 by 6. So, this is only 6 milliampere. This will be equal to 6 milliampere. Whereas the current I2 flowing through the resistance R2 is going to be equal to R1 upon R1 plus R2 into I. R1 is 2 kilo ohm divided by R1 plus R2 is 6 kilo ohm multiplied by the total current I drawn from the source is 9 milliamperes. So, this is 18 divided by 6. So, this is equal to 3 milliamperes. So, the current flowing through resistance R1 is 6 milliampere and that flowing through the resistance R2 is 3 milliampere. So, if we take the sum of I1 and I2, that is 6 plus 3 is 9 milliampere and this is nothing but the total current I drawn. So, in case of the parallel circuits, it is observed that the currents flowing through the different branches of this network which are parallel to each other, sum of the currents flowing through the different parallel branches is equal to the total current I drawn from the source. And in case of a series circuit, we have seen that the potential drops across the different resistors connected in series is found to be equal to the applied voltage. The sum of the voltages across the different resistors is equal to the applied voltage. So that is about the current divider circuit. Now, if let us see the concept of open and short in the given parallel circuit. So if the open appears in the parallel circuit, if open appears in the parallel circuit, what will happen? Let us consider the open appears in this first branch containing the resistance R. If the open appears in this first branch of this parallel circuit containing the resistance R1, then this resistance R1 goes out of circuit and only the resistance R2 remains in the circuit, so that whatever the current is drawn from the source, all that current flow through R2 and there is no current flowing through the resistance R. Or else, if the open appears in this second branch containing the resistance R2, then whatever the current is drawn from the source, all that current will flow through this resistance R1 and no current will flow through the resistance R2. On the other hand, if this open appears in the main circuit itself, if the open appears in the main circuit itself, then there will be no currents flowing through the resistors R1 and R2 because no current will be drawn from the source in this case. Because the main circuit itself, in the main circuit itself, the open appears. The resistance of this open terminals is as always infinite. So no current is drawn from the source. If no current is drawn from the source, no currents will flow either through the resistors R1 or R2. So that is how this if the open appears in the parallel circuit. So depending on the position of the open in the given circuit, parallel circuit, we have the different situation. Now let us see the concept of a short in the parallel circuit. Say we have a source of EMF and the three different resistors R1, R2 and R3 are connected in each other. So this is R1, this is R2 and this is R3, and we have put a short across this resistance R. If a short is put across this resistance R. If such short is put across this resistance R3, what will happen? What will happen? So, if such a short is put across this resistance R3, it is not that only the resistance R3 is short circuited, but as well the resistors R1 and R2 also gets short circuited. So that it means that if the short is put across this resistance R3, this short appears across this source of EMF itself, and in such situation, this source of EMF, from this source of EMF, tremendous current will be drawn, and this source of EMF may get permanently damaged. So, a care must be taken that by no chance a short is put across the parallel circuit. No short is put across the parallel circuit or in the parallel circuit, because in such case all the three resistors gets short circuited, so that this source of EMF is directly short circuited and excessive current will flow through the circuit and the source of EMF may get damaged. So that is about the short appearing in the parallel circuit. So that is about this current divider circuit. So let us see how to analyze this series and parallel circuits. Analyzing a series parallel circuit. On many a number of occasions, it is more advantageous that the given circuit is simplified and is converted to a single resistor circuit. Is converted to a single equivalent resistor circuit. So, if we have the given circuit arrangement like this, we have this resistance R1 and R2, R3 and resistance R3. So this is R1, R2, R3 and R4. And we have a source of EMF. So take the value of the resistance R1 is say 2 ohm, but R2 is 3 ohm, R3 is 6 ohm and R4 is 1 ohm. The values of these resistors are 2, 3, 6 and 1 each. The total current I will be drawn from the source. The total current I will be drawn from the source. So, when we want to find out the total current drawn from the source, or what are the currents flowing through these resistors R2 and R3, what we should do is that first we have to simplify this circuit. So to simplify this circuit, what we need to do is first we have to find out the equivalent resistance of this parallel combination. We have to find out the equivalent resistance of this parallel combination. So if R equivalent is the equivalent resistance of this parallel combination of R2 and R3, then these two resistors can be replaced by a single resistance R equivalent, so that this circuit will take the form like this. This is R1, this is R equivalent, and this is R. This is R1, this is R equivalent, and this is R. So now again we can find out the equivalent resistance of the series combination of R1, R equivalent and R4 and can be replaced by a single resistor like this. So this R is nothing but equal to R1 plus R equivalent plus R4, and this R equivalent is equal to the equivalent resistance of the parallel combination of R2 and R3. So let us find out first the value of in this case, if I is the current drawn from the source here, where is I the current drawn from the source? This current I drawn from the source in all the three situations remains C. So how? Let us for that purpose, R equivalent is the equivalent resistance of the parallel combination of R2 and R3, and this is nothing but equal to R2 R3 upon R2 plus R. So this is equal to R2 is 3 ohm, R3 is 6 ohm divided by 3 plus 6. So it is 80 divided by 9. So this is 2 ohm. It is 2 ohm. So the equivalent resistance of this parallel combination of R2 and R3 works out to be equal to 2 ohm. So here R1 is 2 ohm, R equivalent is 2 ohm, and R4 is 1 ohm. So that the total resistance R of the circuit works out to be equal to R1 plus R equivalent plus R4. So this is 2 ohm plus 2 ohm plus 1 ohm. So this is 5 ohm. 5 ohm is the total resistance of the circuit or network. So if 5 ohm is the total resistance of the circuit, then what will be the current I drawn from the source? The current I drawn from the source is V upon R. V is 10 volt and R is 5 ohm. So this is 2. So the total current I drawn from the source works out to be equal to 2 ampere. Now, when this current of 2 ampere flow through this resistance R1 and Ri at this junction, part I1 say flow through the resistance R3 and part I2 flow through the resistance R3. How to find out these currents I1 and I2? To find out the currents I1 and I2 flowing through the resistors R2 and R3, again we can make use of the proportionate, inverse proportionate formula for the currents. So the current I1 flowing through the resistance R2 is equal to R3 upon R2 plus R3 multiplied by I, total current from the source. So this is R3. R3 is 6 ohm divided by 3 plus 6 into the total current I drawn is 2 ampere. So this is equal to 6 into 2 is 12, 12 divided by 9. So this is 12 ampere. So this is 1.33 ampere. The current flowing through the resistance R2 is 1.33 ampere. However, the current I2 flowing through the resistance R3 works out to be equal to I2 is equal to I2 is equal to R2 divided by R2 plus R3 into R. R2 is 3 ohm divided by R2 plus R3 is 9 ohm multiplied by I is 2 ampere. So this is 6 by 9. So this is 0.67 ampere. This is 0.67 ampere. So the current flowing through R2 is 1.33 ampere and the current the sum of these two currents works out into the total current I from the source. And knowing these currents flowing through the resistors R1, R1 and the total current flowing through the resistors R1 and R4, we can find out the voltage drops across the resistors R1, R2, R3 and R4. So let us find out the voltage drops across the resistors R1, R2, R3 and R4. See here, PD across R1 is equal to I into R1. I is 2 ampere, R1 is 2 ohm. So this is 4. The potential drop across the resistance R1 works out equal to 4. PD across R2 will be equal to I1 into R. PD across R2 will be equal to I1 into R. So I1 is 1.33 ampere multiplied by R2 is 3. So this is equal to this is equal to 3.99. Then PD across R3 will be equal to I2 into R3. So I2 is 0.67 into R3 is 6 ohm. So this is equal to 4.02. It is 4.02. So here what we have is that the resistors, since R2 and R3 are connected in a parallel to each other, the potential drops across R2 and R3 will not have the two different values. The very most important point that you must remember here is that since the resistors R2 and R3 are connected in a parallel with each other, the potential drops across R2 and R3 will not have the two different values, but the potential drops across R2 and R3 each will have the value of 4. Each will have the value of 4. And the potential drop across R2 will be equal to I into R4. I is 2 ampere into R4 is 1 ampere. So that if we calculate the sum of these potential drops, if we calculate the sum of these potential drops, it works out to 4 volt plus 4 volt plus 3 volt. So this is 10 volt and this is the right of voltage. This is the right of. So when we have this voltage of 10 volts applied across this series parallel combination, then a potential of 4 volt is dropped across R1, a potential of 4 volt is dropped across the parallel combination of R2 and R3, and a potential of 2 volt is dropped across the resistance R4, such that the sum of the potentials across R1, the parallel combination of R2 and R4 is equal to the value of the applied voltage. So that is how we can analyze the series parallel circuit. That is how we can analyze the series parallel circuit. And next we want to discuss is the Thevenin theorem, Norton theorem and superposition theorem and maximum power transfer theorem. That will continue in the next video. Thank you.